So today we are going to be solving Cambridge International AS and A Levels Chemistry Paper 1 Multiple Choice, May June 2025 and Paper 12. So basically we're going to be solving this paper in two parts. The first part is going to have the first 20 questions and the next part is going to have the next 20 questions. Why is that so? Because A Levels paper they're a little bit technical. Okay? They need understanding. They cannot just be you can check out the marking schemes for the correct answer, but I want to tell you the absolute concepts behind every answer. They're technical. They cannot just be like, I cannot just say that C is the correct answer or D is the correct answer. No, that's not the way you solve an A levels paper. In A levels, you should have the exact understanding why is that the specific answer. Why you need exact understanding? Because look, A levels is not something that you can do without understanding. Definitely, you need understanding of everything. O levels, if you rote learn things, you can succeed somewhere. But in A levels, you need understanding. So let's get started. Okay. Question number 1 says, consider the following statements. Silicon dioxide has a higher melting point than sulfur dioxide. That's simple. You should know why. Because silicon dioxide is a giant ionic or giant covalent structure. You should know the formula. It is basically SiO2. And what is sulfur dioxide? Sulfur dioxide, you should know the formula. It is SO2. Sulfur dioxide is a simple molecular structure. Okay? These things are important. You guys should know it. Recently, examiner is just fond of bonding. I don't know why he's testing bonding a lot in A levels papers. Simple molecular structure. Okay, ammonia has a higher boiling point than phosphine. Okay, so basically, consider the following statement. Now we need to tell which statements are correct. First statement we just saw and we thought it is correct because silicon dioxide is basically a giant covalent structure. And we know that since it's a giant covalent structure, it's gonna have strong covalent bonds that we need to break in order to melt it. And since it's a giant covalent structure and there's strong covalent bonds in it that we need to break, that we need to overcome, it's going to have a high melting point. And sulfur dioxide, since it's a simple molecular structure, it's going to have a low melting point. Okay? So this statement is correct. Next, ammonia, not ammonium, has a higher boiling point than phosphine. So to consider the boiling points of ammonia and phosphine, we need to draw the structures, look at all the intermolecular forces present. So ammonia is NH3, something like this, and phosphine is PH3, something like this. Both have a lone pair on top. Okay, both have a lone pair on top. Now, these two pictures might make you think that both of them should have equal boiling points, or phosphine in that case should have higher because it has more number of electrons. Because if you check, phosphorus basically has 15 electrons, whereas nitrogen has 7 electrons. You might think this, so phosphorus should have more induced dipole, but you are at the wrong track. Why? Because look, if we count the intermolecular forces in phosphine, the first intermolecular force is induced dipole, and that is because of the electrons. Okay, the second intermolecular force I can think of is permanent dipole. And why do I have a permanent dipole? Because this is a polar molecule. We know it's polar because it's not symmetrical, it's not tetrahedral, it's not a simple planar molecule, it's not trigonal planar, it's trigonal bipyramidal. And since it's trigonal bipyramidal and the dipoles, they don't cancel out. Look, the dipole, this is the dipole, this is the dipole, this is the dipole. All these three dipoles, they don't cancel out each other. This is a trigonal bipyramidal molecule, so it's going to have permanent dipole forces. And for over here, phosphine is going to be having a partial negative charge, and these hydrogens, they're all going to be partial positive. So there's going to be a permanent dipole, and that is because of the dipoles induced in it. Now, these are the only two forces that are present over here. But ammonia has 3 types of intermolecular forces, and it has the strongest intermolecular forces. Obviously it is going to have induced dipole and permanent dipole, similar case, but it's going to have another force that is called the hydrogen bonding. Ammonia is going to have hydrogen bonding, and hydrogen bonding is the strongest type of intermolecular force that is present. ठीक है, strongest type of intermolecular force. Why ammonia is going to have hydrogen bonding? Always remember, whenever hydrogen is bonded to either oxygen, nitrogen or fluorine, it's gonna form hydrogen bonding. ठीक है, it's gonna form hydrogen bonding. And what's hydrogen bonding? Basically, this partial positive hydrogen is attracted towards the lone pair that is present on an other ammonia molecule, something like this. So there's an attraction between these two. So that's hydrogen bonding, and that's the strongest type of intermolecular force. Hence, phosphine does not has hydrogen bonding. Why? Because hydrogen is not bonded to nitrogen, oxygen or fluorine. But ammonia has hydrogen bonding. So ammonia is definitely going to have a higher melting point, a higher boiling point than phosphine. So statement 2 is also correct. Both statement 1 and 2, both are correct. So it's going to be option number A. And I hope you understand it, because just knowing the answers, it's not going to give you the skill to solve a question. You need the understanding behind it, the bonding behind it, all that I told. Okay, moving on to the next question. How many neutrons are contained in an atom of iron with a mass number of 60? Okay, so that's simple. That's very simple. Mass number of 60, you need to calculate the neutrons. When you have questions like these, you have questions like these as well, which are going to be solved in second. It's simply going to be, since the mass number, which is the nucleon number, it's 60 minus the proton number. Go to the periodic table, check out the proton number. So where is our iron? This is iron. This is the proton number. Okay? This is the proton number. Some of you might think, what is this? This is the nucleon number, right? This is the nucleon number, but that is the relative atomic mass, meaning the mass of all the isotopes combined. This is the relative atomic mass. If you try to outsmart the examiner and do 55.8 minus 26, you're gonna straight away it's gonna be cut. No, you cannot do this. You cannot outsmart the smarter. Okay? Examiner is simply smarter than you. You cannot do this. Okay? Don't try to do this. He's told you that you have to find the number of neutrons in the isotope that has 60 mass number. Don't think this is the mass number. Please don't do this. 26 is going to be your proton number. So let's go to the beginning. 26 is the proton number. So we're in no hurry. 60 minus 26 on the calculator. Let's see what we get. 60 minus 26, and that gives 34. So there are going to be 34 neutrons in it. Okay. Next, the diagram shows a Boltzmann distribution for molecular energies for a gaseous reaction or at two different temperatures and two different activation energies. Okay. So now this is temperature 1 and this is temperature 2. This is the activation energy for the first reaction, I guess, and this is for the second reaction. This is the proportion of molecules. This is the energy. Which combination of temperature and activation energy will give the highest rate of reaction? Okay. Always remember, lower activation energy, lower EA means you're going to have a faster reaction. Why are you going to have a faster reaction if you have lower EA? Because simply, the more energetic the molecules, the faster the reaction. I get it. But the lower the activation energy, the faster the reaction. Because look, in the second activation energy, only the particles that are on the right side of the activation energy, which is this much of particles, only this much of particles will react. Okay? I'm highlighting this with a blue color. Only this much of particles. Okay? You see, only this much of particles is gonna react. But if we talk about the second EA, you know how much of particles will react? I'm highlighting it with the red color. This much of particles will react. This much. Including this as well. So this much of particles will react. So now you can see it for yourself. For the blue one, it was only this. And for the red one, this. Only the particles that have energy more than the activation energy are going to react. So that is simple. If only the particles that have more than the activation energy are going to react, we need a lower activation energy. If this is the activation energy, this for instance, then these many particles will react. So the lower you make the more backward you move with the activation energy, the more particles will react. So definitely I need the EA1 activation energy, that is backward. So it's going to be EA1 and EA1. Now it's simple. I need molecules to react more. Okay? So I need a temperature that is higher. Why higher? Because look, if I have the curve number 2, these are the particles beneath curve 2 that are gonna react. But if God forbid I have curve number 1, this curve, what particles are beneath it? Only these particles are beneath it. Only these particles. But for the second curve, for the second temperature, all these particles were beneath it. So you get it. More particles are gonna be more energetic when you have a higher temperature, hence you're gonna get a faster rate. So we're definitely looking for the second temperature. So it's gonna be the second temperature, which makes option D the correct choice. I hope you get it. Okay. If you don't get anything, you can ask. The reaction between sulfur dioxide, okay, you have sulfur dioxide and oxygen has the equation shown. You have 2 moles of sulfur dioxide, make it react with oxygen, forming 2 moles of sulfur dioxide. It's definitely a negative enthalpy change reaction. 1 mole of SO2 and 1 mole of O2. Okay, 1 mole of SO2, 1 mole of O2 are placed in a closed container and heated to a constant temperature. At this temperature, 0.8 mole of SO3 are present in the equilibrium mixture. Which statement is correct? Okay, so now let's see. The equilibrium partial pressure of SO2 is greater than the equilibrium partial pressure of O2. We need to find out the moles. First, let's see. The Kp has units of mole per dm cube. That's incorrect. That's incorrect. I'm going to tell you. At a lower temperature, the equilibrium amount of SO3 is lower than 0.8. At a lower temperature, equilibrium is going to move forward. So if equilibrium move forwards at a lower temperature, the equilibrium amount of SO3 is going to be actually higher than 0.8. 0.8 is right now. If we lower the temperature, it's going to move more forward. And if it moves more forward, you know what's going to happen? Obviously, the yield is going to increase. So that's also incorrect. The mole fraction of SO3, the mole fraction is less than 0.8. Okay. Let's check it out. So now we have option A and D that we have finalized, and for that we need to find the moles. So let's make our ice table, our beautiful ice table. We have 2 moles of SO2. Hard work is the way out. You need to work hard. So I believe you should draw this table. It's definitely worth it. Even it's a 1 mark question, but definitely draw it. Okay, so you have 0.1 mole of this stuff, 0.1 mole of this stuff initially, and you have 0 moles of this initially. You have not formed any SO3, and at equilibrium beta, you have 0.8 moles of this. If you have 0.8 moles of this, definitely you have formed 0.8 moles of this. And if you have formed 0.8 moles of this, that means since look at the equal ratios, 2:2. Don't look at this 1 ratio right now, just to make things clearer. If you have formed 0.8 moles of this, then you've used 0.8 moles of this. So it's gonna be a negative 0.8 here. It's not 0.1, it's 1.0. So this is 1.0. That is what I was thinking, that how is it possible that you take out 0.8 out of negative 0.8. And since it's 2:1, so if this is half of this is, if it's u 0.8, this is gonna be half use. It's 2:1. I'm clarifying everything over here because I need absolute clarity in the concepts. Okay, it's gonna be plus 0.6 over here, it's gonna be plus 0.2 over here, and your partial pressure. What's gonna be your partial pressure? Do we have the volume? We don't have the volume. It's fine, we don't even need the volume. Let's find out one thing. The mole fraction of SO2 is less than 0.8. Let's find out the mole fraction. Mole fraction, for mole fraction, the simple formula, you have total moles as your denominator and the moles that you're finding, moles that you are trying to find, matlab the of that specific thing on the top, that's simply a mole fraction. So at the bottom we have the sum of all moles. It's going to be 0.8 plus 0.6 plus 0.2. So it's going to be 0.8 plus 0.6 plus 0.2, 1.6. 1.6, I'm trying to find the mole fraction of this, so it's going to be 1.6 upon 0.8. Let's see, 0.8 divided by 1.6, and that gives me 0.5. So I have 0.5 as my mole fraction. The mole fraction of SO3 is less than 0.8. That's correct. My mole fraction is coming out to be 0.5, which makes my option number D as the correct answer for question number 4, because I just calculated it in front of you guys. I didn't had the pressure, I didn't had the total pressure, so I could not check my option 1. But I didn't even need to. Look, if you're correct, you're correct. No matter you don't check an option. If you're dead sure about one option, it's fine. I didn't had the pressure. I didn't even needed the pressure. Look, I figured out the correct answer without the pressure. Okay? So some people might be stuck on the first option, thinking that how do we figure out the partial pressure? How do we? Don't do it. If you can't find the way out, it's fine. There are 3 more options. So when you have 4 options, you have a 20% probability that either one of them can be correct. So even if this 20% was gone, try to think it in a mathematical way, you still had a 60% opportunity or percentage that you could get the right answer. Not 60, sorry, 80. So not, oh no, it's not, oh, I thought it was 5 options. 5 options where you have a 20%, but in this it's about like 22 something percent, but still you have other options. Okay, red lead is a red pigment with the formula Pb3O4. This is quite unfamiliar to us, but it's fine, we're going to figure it out anyway. Every formula unit of red lead is the same. Okay, so that's the formula unit, and every formula unit is the same. Each formula unit contains 3 lead ions and 4 oxide ions. Okay, now they're emphasizing on one thing. Every formula unit is the same. Lead has 2 different oxidation states in red lead. What are the oxidation states of lead in red lead? Okay, so now we can have 2 different oxidation states and we should be ready for it. It is basically Pb3O4. To figure out the oxidation states of lead, we need to figure out the oxidation state of one more thing. That is our oxygen. For oxygen, one oxygen has an oxidation state of 2 negative. And we have 4 oxygen. So multiplied by 4, that's a negative 8. To balance out a negative 8, what do we need? To balance out a negative 8, we simply need a positive 8. So how can we make a positive 8? Think about it. Look up. We need to use our minds. We need to use our minds. The perfect thing I can say for an A-level paper is just calm, relax, and rest, because you need to use your minds a lot. Because these are questions no one has practiced ever. They're not gonna come from like a lot of practice. They're gonna come by thinking. You need to have good thinking skills. Now we have three leads. Okay, we have three leads. So for the first one, now if I say two of my leads are positive one, to get two of my leads, they're gonna be positive one, and one lead is gonna be positive two, or what could happen is two leads are positive two, and one lead could be positive one. Okay. For B part, two leads are positive one, and my third lead is gonna be positive three, or two leads could be positive three, and the third lead could be positive one. In the C part, two leads could be positive 2 and one lead could be positive 4, or two leads could be positive 4 or one lead could be positive 2. In the third part, two leads could be positive 2 and one lead could be positive 6, or two leads could be positive 6 or one lead could be positive 2. Okay, I've written down all the possibilities. Now for the first one, the answer, what kind of answer am I expecting? I'm expecting an answer of a positive 8. That is all I need from lead. Okay, over here if I solve this, I get a 2 3 4. Over here I get a 1 2 3 4 5. Definitely not option A. Okay, if I come to option B, I get 3 4 5, and over here I get 3 plus 3 6 and 7. Definitely not option B. If I come to option C, I get 4 5 6 7 8, and over here I get 4 plus 4 8 9 10. I get a 10. Okay, and if I was looking for a positive 8, which I got over here, but still I let me tell you guys. In option D, I get 6 7 8 9 10, and 6 plus 6 12 13 14. Where do I get a positive 8? Where do I get a positive 8? In option number C. That was simple, that I just needed a positive 8. Okay, that means this combination, this deadly combo of 2 2, this means two of my leads are positive 2 and one lead is positive 4 in this PB304. Okay, I hope that makes sense. I just did every possible thing I could to make you explain this. Some standard enthalpy change of combustion data are given. You have carbon, and standard enthalpy change of combustion means that you add oxygen to it, form carbon dioxide, and that is the amount of energy that's going to be released. Why not carbon monoxide? If any one of you could tell me why. Because carbon monoxide is not going to be the standard enthalpy change of combustion, because remember that standard enthalpy change of combustion is when 1 mole of a substance is formed by burning it in excess oxygen. If you give carbon excess oxygen, it will never form carbon monoxide. Okay, hydrogen, you add oxygen to it, it forms H2O, and this is the energy released. CH3OH, which is your methanol, you give oxygen to it, it forms carbon dioxide and water. Okay, what, using these data, what is the enthalpy change of formation of methanol? Okay, you need formation of methanol. Now let's draw a Hess cycle to make us understand things. What do we have? We have methanol, okay, CH3COH. That's not methanol, that is ethanol, CH3OH. And out of it, we're forming carbon dioxide and water. And below, in the below column, we have, what do we have? We have elements like carbon, oxygen, hydrogen, we don't care, whatever is below. And when we form carbon dioxide, we combust carbon in oxygen and form carbon dioxide. How much heat do we release? We need to balance this equation as well. Balancing is a essential part of this equation. So first let's balance it out and then see how much heat is going to be released. There's going to be a 1 2 3. Okay, there's going to be oxygen. We're not going to balance the oxygen, definitely not. So balancing the hydrogens, there's going to be just a 2 over here. Okay, so now when we're going to form carbon dioxide, how much energy are we definitely going to release? It's negative 394. And when we are going to form water, how much energy are we going to release? It's going to be negative 286, but negative 286 is going to be multiplied by 2 because we're forming 2 moles of water. Don't forget this. We don't know the formation of delta H, formation of this methanol. For oxygen, we know it's going to be 0. We don't even need to balance it out. And now we need to, and for this thing, for this, from going from methanol to carbon dioxide and water by burning it, is going to be negative 726. So this is negative 726. Okay, so now what are we gonna do? We're simply gonna make 2 roots. The first root is gonna be from here to here. This is our end. And the second root is gonna be from here to here. Okay? Now we're gonna equate the 2 roots. The first root equals to the second root. We need to find this. This is delta H naught of formation of methanol, which is this arrow. So delta H naught of formation, you know, for the first root, which 2 values do we have to take? We need to take this value and this value for the first root. And the second root involves this value and this value. So now we're going to take the values of the first root, which is delta H naught of formation plus negative 726 equals to my second value, which is going to be negative 394 negative 286 times 2. If I just try to solve it, is gonna be delta H formation equals to negative 394 negative 286 times 2 positive 726. And let's see what answer do I get. Okay, it's negative 394 then negative 286 times 2 positive 726, and I get negative 240. Option A is gonna be my answer, and I hope this method is clear to you. Next, which row is correct? Smallest bond angle to the largest bond angle. Okay, so H2O, what's gonna be the bond angle? That should be on your fingertips. It's 180 degrees. BF3, what's gonna be the bond angle? Trigonal planar. NH3, trigonal bipyramidal. Trigonal bipyramidal, what's gonna be the bond angle? There's gonna be something like, because initially it had to be 109. Okay, you have N, you have a lone pair here, and then you have 3H like this. It had to be 109, it had to be 1 of 9 if this was a bond pair, but this is a lone pair, so now it's gonna be 107 degrees. So this is 107 degrees, H2O is again 180 degrees, NH3 is 107 degrees, 107 degrees, 180 degrees, 120 degrees. BF3 is trigonal planar, you know it. 107, this is gonna be 120, 180 and 120. Now just simply see where are we going from the smallest to the largest. Is water gonna be definitely 120? That was a trick that I was playing, and you guys just fell into my trick. To check your concept, water was never 120. I just said it in the flow. This was just to make you guys realize, would you guys like think about it or not? And if you didn't, that means your preparation is not good. What is not 120? How can it be 120? That is the major misconception people have. Water is even less than ammonia because it has 2 lone pairs. I don't know why people miss this out. 2 lone pairs on water like this. This bond angle is approximately 104.5 because of these 2 lone pairs that are pressing down on the hydrogen. The angle decreases to 104.5. So water was 104. And if you guys didn't realize this, this was just a reality check to you guys. Now check the correct answer. and it is A, I guess, right? Because in A we're going from the smallest to the largest. Okay, in the Haber process, the reaction between the two gaseous reactants requires the use of a catalyst that contains a transition element. We know we use, what's the Haber process? We have our nitrogen, we have a 3 moles of hydrogen, and we form 2 moles of NH3. And what type of catalyst do we use to catalyze this reaction? We use iron. Ferron, it's also called ferron, but like, no. It's gonna be iron, and that is Fe. So it's gonna be Fe. And what metal and what is the mole ratio do gases react? It's 1:3. We have 1 mole of nitrogen, we have 3 moles of hydrogen. So it's gonna be option B, that's gonna be correct. Question number 9 says aqueous hydrogen peroxide decomposes into water and oxygen in the presence of a suitable catalyst. Okay, catalyst can be anything. It can be catalase, enzyme, or any catalyst. Okay, we don't know about the catalyst, but we know that what's happening is that we have H2O2, which is hydrogen peroxide, that is decomposing, and it's not a reversible reaction. It's an irreversible reaction right now, okay, into oxygen and water. And if we balance out this equation, we're going to put A2 over here and I guess A2 over here. Now we have 4 hydrogens on this side, 4 hydrogens on this side, and 4 oxygen on this side and 4 oxygen on this side. So this is a balanced equation of the decomposition that is happening over here. Okay, this might be tricky, challenging to some of you guys, so listen to this carefully. You have 50 cm cube of 0.5 mole per dm cube of a solution of hydrogen peroxide, and you're producing 120 cm cube of oxygen out of it. Okay, so that is what you have, and that is what you're producing out of it in 2 minutes. Okay, so the time that is being taken is 2 minutes. The volume of the gases was measured at room conditions. What is the average rate of decomposition of hydrogen peroxide during this 2-minute period? Okay, the rate of decomposition means that your change in concentration that is happening, change in concentration of H2O2, that is changing because you're producing oxygen out of it over the time taken. Time taken, you all know it's going to be 2 minutes, and that is what we know, 2 minutes. And since in the options the time is given in seconds, so we're going to convert it into seconds. Why? Because if we use minutes, we're not going to get the correct option. So 2 times 60, that is 120 seconds. Okay, we know the time, but we don't know the change in concentration. So how do we find the change in concentration? How do we know that how much of our hydrogen peroxide decomposed? For that, we know how much oxygen was formed. Okay, so we're going to find out the moles of oxygen that decomposed, that was formed, and from that we can figure out the moles of H2O2 that decomposed, because 1 mole of oxygen is going to be formed from 2 moles of H2O2. So let's find the moles of oxygen. So moles of oxygen is going to be volume, which is 120 divided by 24,000. Okay, why 24,000? Because it is in cm cube. Okay, when it's in dm cube you divide by 24, when it's in cm cube you divide by 24,000. So 120 divided by 24,000, 120 divided by 24,000, and that gives me 0.005 moles of my oxygen gas that was produced. Now oxygen, what I need, I don't care about oxygen, I care about hydrogen peroxide, because I need to find the rate of decomposition of hydrogen peroxide. I need to look how many moles of hydrogen peroxide were used. Okay, I need to find out that change. So I need to see if 120 cm cube of oxygen was formed, then how much of my moles of hydrogen peroxide were used in this. So it's 1:2. So if 0.05 moles of oxygen were formed, double the moles of hydrogen peroxide were used. So 1:2. So this means that if I say moles of H2O2, they're going to be double that of 0.005 times 2, and it's going to give me 0.01 moles. So I need to convert my moles of H2 O2 into concentration. How do I convert moles into concentration? I guess that's simple enough. Concentration equals to moles divided by the volume. Now, moles I know they're 0.01. The volume is 50 cm cube. How is it 50 cm cube? It's given to me. It was initially 50 cm cube and it's going to remain 50 cm cube. So the volume is going to be 50 cm cube. And if I take it in dm cube, it's going to be 0.05 dm cube. 1, 2, 3. So it's 0.05. So 0.01 divided by 0.05. Let's check what we get. 0.01 divided by 0.05 and we get 0.2 mole per dm cube concentration. That is the change in concentration that we get. 0.2 mole per dm cube concentration changed. Okay, don't think that's the final concentration. No, that's the change that's happening. The final is gonna be 0.5 minus 0.2, that's going to be 0.3. This is the change divided by the time in seconds, that was 120. Let's check what we get. 0.2 divided by 120 and that gives me, so the answer comes out to be 0.001 and if we round off this 6, it's going to be 7. So 0.0017 is the answer, equals to 0.00166, and if we round it off, it's going to be 17, which is option number C. I hope you understand why we get option number C and not option number A, B, or D. Okay, moving on to the next question, which says that the average intermolecular forces in water are stronger than the average intermolecular forces in steam. Okay, so water has more intermolecular forces. What kind of forces are we talking about? Primarily hydrogen bonding. Okay, that's the intermolecular force that we have in steam and water. They're stronger in water. Obviously, they're going to be stronger in liquid than in steam. The average intermolecular forces in ice are slightly stronger than the average intermolecular forces in water. So ice has stronger forces than water. Obviously, we know that intermolecular forces are greater in solids compared to liquids and greater in liquids compared to gases. That is what we know. Enthalpy changes are associated with the equilibrium process as shown. Okay, we're going from a liquid to a gas. We're breaking intermolecular forces. Okay, we're going from a liquid to a gas. We're breaking intermolecular forces. And since the examiner told us the intermolecular forces in water are much stronger, that means they're very stronger than those in steam. So if we're going from a liquid to a gas, we're giving it a lot of heat. So we're giving it a lot of heat. So since we're giving it heat to break the intermolecular forces, this is going to be endothermic because we're giving it heat to break the intermolecular forces. Now we're going from a solid to a liquid. The average intermolecular force in ice are only slightly stronger. Over here, the examiner used the word much stronger. And over here, he used the word slightly stronger than the average intermolecular forces in water. So in ice, this is ice and this is water. They are only slightly stronger, not very stronger. So less heat given. Though this is also going to be endothermic. No doubt in it that this reaction is also going to be your endothermic reaction, but only little heat is given. This is more endothermic, the first one. This is going to be more endothermic. Whereas the second one, this one, it's going to be less endothermic. And I hope you understand why. Delta H, B and M are both negative. Why negative? They're endothermic. We're giving it heat to break the intermolecular forces. And we given heat, that's endothermic. So it cannot be negative. It has to be positive. Delta HB is greater than delta HM. Okay, B is greater than M. Yeah, B is going to be greater than M. Why? Because in B, we're giving a lot of heat. Since in water, the intermolecular forces are much stronger. They're a lot stronger. So we're giving more heat. Whereas in ice, the forces compared to liquid are little stronger. So we're giving less heat. So delta HB, we're giving more heat. In delta HM, we're giving less heat. So it's option number 2 is correct, that B is greater. Okay, 3 says the intermolecular forces in ice and water are of the same type. Yes, they are of the same type. In ice, the forces that we're talking about are just your hydrogen bonding. Hydrogen bonding is the main force we're talking about. And what are we talking about in water? The same hydrogen bonding. So this is also correct. 2, 3, it's gonna be option number D. 2 and 3 only. And I hope you get why. The next question. Okay, an experiment is carried out to determine the value of X in hydrated lithium hydroxide LiOH A sample of the solid is heated in a crucible over a Bunsen flame. Complete dehydration takes place. Decomposition does not occur. We're not decomposing it, we're dehydrating it. And we have to find the value of X in this salt. I believe that you should know this formula, that to find out the number of X in the formula, the number of moles of X that would react with 1 mole of lithium hydroxide, you should know this formula by heart, which is you need moles of water divided by the moles of salt. What is the salt in this case? Lithium hydroxide. What is water? It's H2O. So we just need to take the moles of water and divide it by the moles of salt. Okay, so for moles of water, what do we need? What we need to get, stick to the basics. I know these might seem complicated, R, S, Q, it's fine. Stick to the basics. We need mass of H2O divided by the MR, which is 18. Okay, these are moles of water. These are moles of water divided by the moles of salt. Okay, divided by the moles of salt. What are going to be the moles of salt? It's going to be mass of lithium hydroxide over the MR of lithium hydroxide. Let's find out the MR of lithium hydroxide. It is LiOH. So let's go to the table this below and find out the MR. For lithium, it is 6.9. Okay. For oxygen, it is 16, and for hydrogen, it is 1. So 6.9 plus 16 plus 1. 6.9 plus 16 plus 1, and that gives me 23.9 as my MR. Okay, so 23.9 is my MR. 23.9. That's going to give me the total expression for X. X equals to moles of water divided by moles of salt. I've written down the expression for you. Now you just need to plug in the mass of H2O and mass of LiOH in this equation. What's going to be the mass of H2O? Let's figure out. Mass of the empty crucible is Q, and mass of the crucible with LiOH XH2O is R, and the mass of crucible with residue is S. What's going to be the mass of water? The mass of hydrated salt minus the mass of residue. What is residue? Residue is your dehydrated salt. What is dehydrated? That is lost water. The mass of crucible and crucible will cancel out. The mass of the hydrated salt minus the mass of residue, what is it going to give you? The mass of water. The mass of hydrated salt minus the mass of dehydrated salt, because crucible and crucible is going to cancel out. So what's going to be left? The mass of water. So it's going to be R minus S. It's going to be the mass of water. So mass of H2O is R minus S upon 18. Okay, divided by the mass of LiOH. Now how are you going to get the mass of LiOH? Okay, mass of empty crucible is this, and the mass of crucible with LiOH is this. Look, this is the mass of the empty crucible, and this is the mass of the residue, which is LiOH. So Q and S minus Q. It's going to be simple. It's going to be S minus Q. So for lithium hydroxide, it's going to be S minus Q, which is the mass of lithium hydroxide upon the MR, which is 23.9. Now, what do? For this division sign, we flip it. We take the reciprocal. So it's going to be R minus S upon 18 multiplied by 23.9 upon S minus Q. And if we simplify it, it's going to be 23.9 R minus S upon 18 S minus Q. I guess, what is this expression? A is not like this, B is not like this, C is exactly like this. So it's going to be option number C. I hope how we get it. You understand how we got it. It was simple. I told you the steps. You had to find the MR of water divided by the mass of water to find out the moles of water. Then you had to find out the mass of LiOH divided by the MR of LiOH to get the moles of LiOH. The moles of water, these are the moles of water with blue, the moles of LiOH with red, divided, you divide these two moles, and then you get this. That's simply R minus S minus Q is simply the mass that we're dealing with. A sample of ideal gas occupies a volume of 240 cm cube at 37 degrees Celsius and 100 kilopascals. How many moles of gas are present in the sample? Okay. So now basically we're looking for the moles. So we simply have to use the ideal gas formula, which is PV equals to nRT. We know everything in the formula. It's simple enough. Pressure has to be in pascals. Volume has to be in mole, not in mole, in meter cube, and moles has to be simple. R has to be 8.31 and temperature has to be in Kelvin. So by simply using the formula and putting in all the values in the formula, we can find out anything we can need. Like if pressure is given, we can find the rest of things. If we want anything, we can find using the formula. Only R is something that we always have, that is 8.31. So by just rearranging the formula and making the number of moles my subject and putting my pressure and volume over my R and T, and since I know that I have to use T in degree Celsius, not I have to use it in Kelvin, so I have to add 273 to my 37 degrees Celsius and just put it as it is in your calculator. Let me put it in my calculator and see. So 100 into 10 raised to power 3 into 240 into 10 raised to power negative 6 upon 8.31, and don't forget these brackets, they're very important, into 37 plus 273. That is my conversion into Kelvin from degree Celsius to Kelvin, and I get 9.316 into 10 raised to power negative 3 as my answer, which is option number B. So that was an easy question. Don't get confused between the powers 10 exponent negative 3 or negative 6. That can be really confusing because option number A is negative 6, and you can easily be driven away if you are not very focused and if you're not looking, and that's how examiner tries to confuse you guys by giving very similar options. Like in this case, you can see if someone is like just doing it randomly, he might select option A because that's the first option. You just see the numbers, you don't focus on the exponents. Moving on to the next question. Under certain conditions, CCl4 and H2O react as shown. Okay, the activation energy for the reaction is plus 62 kilojoules per mole. This means that we require plus 62 kilojoules to initiate the reaction. Okay, the reaction is not going to happen unless and until we give 62 kilojoules of energy. So to start this reaction, we need to give this much energy, and then the enthalpy change is negative 61.5. That means when the reaction happens, this is an exothermic reaction and 61.5 degrees Celsius energy is released, and the negative sign tells us about the exothermic. Now, looking at the graphs, you can simply see which of them are endothermic, in which the products are above the reactants are going to be endothermic. So we simply cross them out. Now we have two, option number A and D, and we have to figure out that which is going to be correct. Now you need to look at something that's very important, the activation energy, that is plus 62. So you need 62 kilojoules per mole for the activation energy. And if you label in A the reactants, and you see that activation energy is going to be from the reactants to the top in A and D, if you label 62 kilojoules, you can see it for yourself. And then when you label the enthalpy change, that is negative 61.5, just look at it and you're gonna get the answer yourself. Look at it. In A, you can see something very strange, that the arrow for 62, the activation energy is very small. If 61 is this long arrow, then how can 62 be only this? 62 should be more than 61.5. So this activation energy, the arrow needs to be longer. It cannot be this small. So that is incorrect. This is not possible. 62 has to be a longer arrow. And that is what we can see, that this is impossible. If we look at option D, that is correct. The arrow is at least the size of the enthalpy change because they're similar. That's why it's going to be option D. It could be really confusing, but just the size of the arrow was here enough to tell you that 62 at least has to be something bigger, like at least equal to the enthalpy change or greater. Moving on to next question, which was like found difficult by some student, but it was interesting. Okay, so a helium ion contains 2 protons, 2 neutrons, and 1 electron. So what's examiner trying to tell over here is the composition of a helium ion, like what kind of things a helium ion has. Okay, we know it contains protons, neutrons, and electron. A helium ion and a proton are passed separately through a uniform electric field. So you need to realize one thing, that a proton has a positive 1 charge, and helium ion, if we talk about the mass, helium ion has 2 protons and 2 neutrons. So it has four times the mass of a proton and a positive 2 charge, because neutrons are chargeless. So a helium ion has a 4 mass and 2 positive charge. And when we start from this point, you need to realize one thing. When you are lighter, you are bent more. Okay? And the second thing, you should know that like charges attract. No, sorry. Like charges repel and unlike charges attract. So a positive charge is gonna be for sure attracted by the negative side. These are 2 positive charges. They cannot be attracted towards the positive plate. So these positive charges, they have to move towards 4 and 5, the negative side. And now we need to find that which one is helium and which one is proton. The lighter particle bends more. Okay? The lighter particle bends more, and which one's lighter, the proton or the helium? The proton. The proton has 1 times the mass and helium has 4 times the mass, because it has 2 protons and 2 neutrons. So this makes us realize that the fifth one, it's gonna be the proton, the fifth one is gonna be the proton, and the fourth one is going to be the helium. And the key takeaway in this question is that lighter particles deflect more, okay? And the heavier particles, they deflect less. So let me write it down. Lighter particles are going to deflect more and heavier particles are going to deflect less. You should be like good in these kind of things, like in taking away the key takeaways from question. You should have a diary or anything like that in which you can write like all the key takeaways you get from the questions. They're really helpful when you're revising, because you cannot just go through the entire papers on your exam day and then you just can look over here. So it's gonna be proton 5 and helium ion, it's gonna be 4, which makes option C the correct option. And I hope you get it. If you don't get anything in this question, ask in the comments below and I'd be happy to help. That the heavier one is... Okay, so now we have to calculate the empirical formula and the MR of these two fellas. So to calculate the empirical formula, what are we going to do? If we need to calculate the empirical formula, we need to first calculate the carbon atom. So carbon, 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 and carbon. Now we have to make the hydrogen atoms. So there's going to be 2 here, 2 here, 2 here, 1 here, and no 1 here. Because look, over here the valency of carbon is full. So now we're going to write the molecular formula. It's going to be C12345 it's going to be H. Let's count. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. It's H14. It's going to be O2 and N4. So the empirical formula comes out to be, if we divide this entire thing by 2. So it's 2 1 times, 2 2 times, 4 2 7 times, and 2 3 times. So it comes out to be C3 H7 ON2. Do we see anything like this? Arginine? Yeah, we do. Oh, this is incorrect. Well, this is correct. Now let's calculate the MR. If this is coming out to be MR, then we're good to go. I wish this is the MR so we don't have to work anymore on the second one. So MR is going to be the molecular formula. This one. Don't calculate for the empirical formula. It's going to be 12 times 6 plus 14 plus 16 times 2 plus 14 times 2. It comes out to be 174. 14 times 4. Yeah, it's 174, so it's going to be option number A. Okay, the oxide and chloride of an element X are separately mixed with water. The two resulting solutions have the same effect on litmus. Okay, so the oxide, for instance, any element, it's oxide and it's chloride. They're gonna have the same effect on litmus. What could element X be? For aluminum, if we talk about aluminum oxide, that is amphoteric. Aluminum oxide is gonna be amphoteric. So, and if we discuss about aluminum chloride AlCl3 and we discuss its reaction, what's going to happen is that the chloride of aluminum, when it dissolves in water, so we're not expecting a proper reaction of a gas that's being produced over here. But if we talk about calcium oxide is gonna be basic. Okay, calcium oxide gonna form a solution of calcium hydroxide in water, and that's gonna turn the litmus paper blue. But if we talk about calcium chloride, that's an ionic solid. That's not gonna have any effect. Same goes with sodium as with calcium. It's gonna be phosphorus. Why it's gonna be phosphorus? Because when you're adding P when you're gonna add P4O10 or you're gonna add P2O5, that's basically phosphorus oxide. That's gonna produce an acidic solution of H3PO4. And if you're gonna take phosphorus chloride, what's gonna happen, and add it to water, you're gonna see HCl gas being produced. So HCl gas and H3PO4 both are acids, so they're gonna turn the litmus paper from blue to red. Okay, why do the halogens become less volatile as group 17 is descended? That's simple. Their number of electrons increase, and when their number of electrons increase, so do their van der Waals. The halogen bond energy decreases. No, the bond energy does not has to do anything with volatility. Volatility or melting boiling points, they have to do with your intermolecular forces, IMFs, not with bond energy. The halogen bond energy, no, not decreases, not increases. The number of electrons in each molecule increase. 100% correct. Because of number of electrons, your van der Waals increase. The van der Waals forces between the molecules become weaker. No, they become stronger because the electrons increase, and van der Waals are because of electrons. Okay, so now we have this question. Compound M is a white solid. It is the chloride of a period 3 element. Okay, so we're dealing with period 3 chlorides and information about some reaction starting with compound M is given. So it's a chloride of period 3. So it can be sodium chloride, it can be magnesium chloride, it can be aluminum chloride, it can be aluminum silicon chloride, it can be phosphorus chloride, PCl4 or PCl5 or whatever. Then it can be, or PCl3, it can be phosphorus chloride, then it can be the rest, they're not going to form chlorides. Okay, leave the rest. Okay, so these are the chlorides that we have. And now what's going to happen is that you have compound M, okay, plus a non-polar solvent. Non-polar means not water. Like non-polar is going to be something organic. I guess it's going to be organic, not ethanol at all. Okay, a non-polar solvent that does not dissociate, basically colorless solution. Okay, ठीक है, अगर non-polar के साथ it's giving colorless, let's see what else is given to us, because on the basis of this one statement we cannot deduce anything right now. Okay, compound M added a little to time to water, steamy fumes Q, colorless solution R. Okay, steamy fumes tells us it is not magnesium chloride, because magnesium chloride does not give steamy fumes. It cannot be sodium chloride. Okay, either it's phosphorus pentachloride or it's aluminum chloride. Okay, that is what we know. Fumes Q tested with moist blue litmus paper turns red. That is means we produce HCl gas out of these two. Okay, solution R plus a few drops of NaOH. Excess NaOH gives a white precipitate. You know what is solution R? It is the remaining solution with aluminum ions, because phosphorus cannot give you a white precipitate. Dissolves to give a, it's A. It's for sure A. The first thing, it's aluminum. you know it's going to be aluminum. Why it's going to be aluminum? Because you get a white precipitate. And secondly, you know it's going to be a chloride of aluminum because of these steamy fumes. Okay, so the next question is about the strontium and its compounds is correct. Okay, so you should know that the solubility of group 2 sulfates decreases down the group, sulfates decreases, and the solubility of group 2 hydroxide OH2M, it basically increases. Okay, so strontium hydroxide is more soluble than barium hydroxide. We need to check the positions of strontium and barium in the periodic table. So this is strontium and this is barium. Down the group, the solubility increases. So barium is going to be more soluble than strontium hydroxide. Okay, strontium sulfate is more soluble than magnesium sulfate. Down the group, sulfate solubility decreases. So magnesium is going to be more soluble. Strontium nitrate has a lower thermal stability than calcium nitrate. No, it has more thermal stability, because as you go down the group, the thermal stability increases. Okay, strontium is a stronger reducing agent than magnesium. Yeah, down the group, the ability to lose electrons. Reducing agent is a property, is the ability to lose electrons. It basically increases. So option D is going to be correct for question number 19, because as you go down the group, the atomic size increases. As the atomic size increases, you can lose that one electron more easily. So I hope you are getting that why strontium is going to be a better reducing agent than all the elements above it. So for 19, it's going to be D. For question number 20, which is the last one for this video, sodium bromide is warmed with concentrated sulfuric acid. Okay, you have sodium bromide and you have sulfuric acid. You know what's going to happen over here. You know that you have sodium bromide, a halide salt, and you are warming it with H2SO4. You know what's going to be the products. Role of the bromide ions. What's going to happen to the bromide ions? Okay, either you can form H2S, or you can form SO2 or simple S. Now what's happened is that bromide ions is going to give electrons to sulfur, because sulfur over here is in its highest oxidation state, which is +6. Okay, it cannot lose more than 6. Now sulfur has to gain. So either sulfur is gonna be this or this. Okay. So now, first things first, bromide ions is gonna give electrons to sulfur, and when someone gives electrons, what do they become? They become a reducing agent. They reduce another, make other gains. So it's going to be this. And change in the oxidation number of sulfur, it's going to be from +6 to +4. Why? Because it's +6 over here. So it's going to be from +6 to +4. Because देखें इसमें +6 है and it's going to go into this. So it's going to be +4. ठीक है? I hope you get this. And that's it for today's video.